Laser beam time. Okay, so we talked about this briefly when we discussed ray optics, but it's also important to talk about it when we talk about wave optics. When light passes through a medium, and we saw this with Snell's Law, we know that that light is going to quote unquote bend. Okay, and in Snell's Law, we did this by firing a laser. It hit a line perpendicular or normal to the surface, and when it went into the medium, it bent towards that. If N1 up here is less than N2 in here, the two different mediums. These are the indexes of refractions here, and we found an equation from this which states that N1 sine of theta 1 equals N2 sine of theta 2. This was Snell's Law, and these angles, if you remember, are from the laser light to the normal line. So that's what we have. It's important to recognize that as we're entering in this higher index of refraction medium, our light is slowing down. Okay, it's slowing down there, and what that implies from the speed of light is, since speed of light is a wavelength multiplied by a frequency, one of these two has to change. And in this case, or in every case, the wavelength has to change, because if you change the frequency, you would change the energy of that photon of light. So as we enter this medium, not only does the speed of light go down, it slows, but the wavelength goes down as well. Okay. And it's important to recognize the fact that when we are in a medium, okay, we're in some new medium that's not air, and air's technically not a perfect vacuum, so it doesn't have an exact index of refraction of 1, but it's pretty much close enough that we consider air as equaling an index of refraction of 1. But if we're inside some new medium, we need to be able to find the wavelength in that medium. And what we can say here is that if we think about this a little bit, we can say that the wavelength inside the medium is equal to the wavelength, and I'm going to call this the proper wavelength, and this is the wavelength inside a vacuum, simply divided by the index of refraction of whatever we are in. Okay, so this is the index of refraction of your new media that you're in with the wave, and that is the wavelength of the light when you're in that medium. Okay, so this is very important, and we're going to see why this is important later on in the wave optics unit. It especially becomes important when we talk about thin film interference, but it's something to keep in mind right now. When we enter new mediums, we are slowing down this light. It is bending, it's refracting for us, and the wavelength changes. So it's a very, very important thing to see what's going on there for us. Okay, so what we're going to do now is we're going to take this idea of interfering light, and we are going to get light to interfere with itself and see something really wild and crazy in our next video. But until then, adios, take it easy.